Let's consider a vector field, let's call it A mu, where mu are the usual space-time indices, so they can go from 0 to 3. And now, of course, this vector might be a function of the space-time coordinates x0, x1, x2, x3, so it might be a function of x, let's say, so x0, x1, x2, x3. But now we are focused on the transformation of the vector field, not of the coordinates, but only on the vector field. If we transform the coordinates by means of some transformation, and in particular an infinitesimal Lorentz transformation of the coordinates, we derive the fact that we can find the so-called generators, and a space-time translation, for example, would be characterized by the momentum vector, whereas it is angular momentum which characterizes Lorentz boosts or rotations. So now we are focused only on the transformation of this vector field. So I will call it delta A mu, which is given by, now I'm going to drop the dependence on x, it is given by A mu, and then we have a small perturbation which is given by a Lorentz, an infinitesimal Lorentz transformation. And I will put a minus sign, but this is not really important. You can also consider a plus, and I will tell you a little bit more about it later. Essentially, if you put a plus, you have the inverse of such an infinitesimal transformation. So this is not really important. It's as if you are considering, for example, in a two-dimensional space, you have a rotation in an anti-clockwise manner, or vice versa. It could also be clockwise, which would be the inverse transformation. But never mind. So here I will put omega mu nu a nu, like this, and now I will manipulate it a little bit more by simple algebra or tensor manipulation. If you want, we have a mu minus I over 2 minus 2I omega mu nu a nu. So this is just simple algebra. I have introduced the imaginary unit and this factor of 2. And now I'm going to use the fact that the infinitesimal Lorentz transformation is antisymmetric with respect to a swap in the two indices mu and nu. So if I change their position, for example like this, we would get a minus. So I'm going to rewrite it a mu minus I over 2 minus I omega mu nu plus I omega nu mu a nu. Now I can also use the Lorentz metric to contract these indices, so I can also write it as omega beta alpha era alpha nu delta mu beta. So you can check that this coincides with this. Now this Kronecker delta is equal to era mu beta if you want, because when we have mixed indices in the Lorentz metric, we get the Kronecker delta. And if you check here, I can write mu and beta without specifying which index comes first, because this tensor here is symmetric. So when I have a symmetric tensor, which depends on two indices, let's say alpha and beta, I can write it like this, or if you want, I can write it like this, or if you want, I can write it like this, because there is no ambiguity since this tensor is symmetric. And then I'm also going to rewrite this in a similar fashion as omega beta alpha era beta nu delta mu alpha. So I can rewrite it as a mu minus I over 2 I minus era alpha nu delta mu beta plus era beta nu delta mu alpha omega beta alpha a nu. And I'm going to define this object here in the square brackets as sigma beta alpha mu nu, like this. Now, this object here satisfies the so-called Lorentz algebra for a finite Lorentz transformation. And I'm going to show you in the subsequent videos that indeed this satisfies the Lorentz algebra, and it is not difficult to check. After all, it is just tensor manipulation, it is just some algebra, and you can do it quite easily. I will do it, but in a subsequent video. Now, let me tell you how to interpret this quantity here. We can interpret this as a matrix because it depends on these two indices mu and nu. And you can see that there is more than one matrix because each matrix depends on these indices beta and alpha. So if we change them, of course, we get a different matrix. But this is a way to interpret this result. And let me tell you that in this case, we have found an infinitesimal Lorentz transformation. But if we want a finite Lorentz transformation, we have to replace this quantity here, which you can see that, we have the identity which multiplies a mu, and then you have another matrix here which multiplies a nu. The finite Lorentz transformation would be of the following form. A mu would be an exponential e to the minus I over 2 sigma beta alpha omega beta alpha, and this object here will be a matrix mu nu, which depends on the two indices mu nu, and then we have a nu here. So if you expand this complex exponential, the first two terms will give you exactly that expression there, which is the infinitesimal part of the transformation, and the finite version of the transformation would be this one. Then, why is this transformation important? Well, this is a generic transformation, a Lorentz transformation of a vector field, but I want to show you one important property of a vector field. In particular, since this is a generic Lorentz transformation, it contains rotations, not just boosts, but also rotations. And I want to rotate the vector by an angle given by 2 pi around, for example, the z-axis. If we rotate a vector by an angle which is 2 pi around an axis, we are going to get back the same quantity, same vector. So we expect that this transformation here should be the identity in this case, right? And indeed, this is what I want to show you now, because this will be different for spinors, because if you rotate a spinor, a so-called spinor, by 2 pi around an axis, you're not going to get back the same thing, the same spinor in that case, but you're going to get minus the same thing. So that's the importance of spinors, which is still something related to a different representation of the same group, which is the Lorentz group. I will show you that as well, but I want to do so in a manner which is a little different from what is usually done in physics and in mathematics, where essentially the transformation rule for spinors is given to you in some way, which might seem difficult at first because you don't see the connection with the transformation of vectors. But actually, let me tell you that there is a connection, some kind of relation, or let's call it appropriately, generalization, which starts from the transformation for a vector field, and then by some kind of generalizations, it is possible to reach the transformation for spinors. So this is something which might help your intuition, and I will show you that, but this will come in a subsequent video. At this point, I want to do this. I want to prove this. So we rotate by an angle which is 2 pi around the z-axis. The matrix which characterizes the rotation is this, omega beta alpha, because this is the infinitesimal Lorentz transformation, whereas sigma beta alpha are the so-called generators of the Lorentz algebra for a vector field. So in this representation, sigma beta alpha is related to vector fields. We will have a similar transformation for spinors, but sigma beta alpha will be characterized by a different representation. Now, omega beta alpha is, or actually with the upper indices omega beta alpha, but never mind. If you want to switch from lower indices to upper indices, you have to multiply by the metric tensor, which is eta, with some indices alpha, beta, nu, mu, whatever, and you have to transform the tensor with the lower indices to a tensor with upper indices, and so on. But never mind, the properties of the tensor remain the same. In particular, this object is anti-symmetric, so if we swap the two indices, we get a minus. And for a rotation in three spatial dimensions, because we have x, y, z, if you want, because we have three directions of space and one dimension of time, right? So these are the three dimensions of space, and the quantity which is non-zero for a rotation around the z-axis is omega 1, 2, which is equal to minus omega 2, 1, and we set it equal to minus 2 pi. So you can also put plus 2 pi if you want. You will get the same thing at the end of the day. This characterizes the orientation of the rotation. But let me tell you just a little bit more about this, in particular about the fact that all the other terms will be zero here. So if you want to consider an infinitesimal rotation of a vector, now let's assume that we consider a three vector, so with three components, because we consider a three-dimensional vector, we are in three-dimensional space, and we have a vector omega, or w, let's call it w, to differentiate it from omega here. So we have a vector which we call w in three dimensions, so we want to rotate it by an angle which is, let's say, theta, around some axis. So let's assume that theta is an infinitesimal rotation. So theta is infinitesimal, it's a very small rotation. The change in w, according to the rules of classical physics, and this is something that, for example, I have derived in a course on rigid body mechanics, but also in classical physics, you get that the change in a vector due to a rotation is given by the rotation vector theta, which is infinitesimal, remember, this is infinitesimal, cross product with the vector itself, where theta is a vector characterized by three angles, theta 1, theta 2, theta 3. These are infinitesimal rotations around the x-axis, the y-axis, and the z-axis. So it's a generic rotation. It's not around the x-axis, it's not around the y-axis or the z-axis. It's a generic rotation around some axis, which has some components along the x-axis, along the y-axis, and along the z-axis. Now, let me tell you that, and this is something that can be proved in classical physics, I have proved it in other courses, I will not prove it here. This can also be written in a similar form, but instead of writing a cross product, you have a rotation matrix, theta, which is anti-symmetric, applied to the same vector w here. The matrix theta has the following form. So it has, of course, zeros on the diagonal because it is anti-symmetric. Then the components theta 1, theta 2, theta 3 are written like this. We have minus theta 3 here, theta 2 minus theta 1. Then, of course, since it must be anti-symmetric, so minus theta 3 here becomes theta 3 under the diagonal. Then we have minus theta 2, theta 1, and that's it. So you can check that multiplying this vector by this matrix gives you exactly this vector cross product with a w. Now, another thing we have to do in order to be able to calculate this matrix is to calculate the sigma beta alpha for vectors. So we have found the expression for sigma beta alpha, which is this one. We also have the indices mu and nu, so actually we have 4 indices, so it might sound a little bit complicated, but let's try to digest it together. In particular, since the only non-zero term in our case will be omega 1, 2 and also omega 2, 1, it means that since we have to multiply sigma beta alpha with omega beta alpha, we are only interested in sigma 1, 2, and also sigma 2, 1, which will be minus this thing because this is also antisymmetric. So this is a matrix because it has the two indices mu and nu, and let's multiply it by minus I because we also have this factor I which we can get rid of. So we have era 1 nu delta mu 2 minus era nu 2 or 2 nu, which is the same because this is symmetric, delta mu 1. Now, how do we calculate it? We can recast this in a matrix form. In particular, this object here can be thought of as the column vector given by 0, minus 1, 0, 0. And then here we have the row vector 0, 0, 1, 0. And why is this? This can be represented as a row vector because mu here represents the rows of this matrix, whereas nu labels the columns. So we describe this as a column vector, like this. Then similarly, we have minus 0, 0, minus 1, 0. So I'm assuming that era has the signature plus 1, minus 1, minus 1, minus 1. And then we have delta mu 1, which can be described by the row vector 0, 1, 0, 0. So if you put them together, you get the following 4 by 4 matrix 0, 0, 0, 0, 0, 0, minus 1, 0, 0 plus 1, 0, 0, and then we have 0, 0, 0, 0, like this. And now, for simplicity, let's just call this a matrix M. And we can rewrite, therefore, this thing here. And for convenience, let's just drop the indices mu and nu. But we have to remember that this thing here is a matrix. And the exponential of a matrix can be interpreted as the Taylor series of this exponential. So we have powers of such matrices which we can interpret. So we have something of the following kind. We have e to the power plus 1/2 times 2, and this factor of 2 comes from considering the fact that we only have two terms in this summation which are non-zero, because we have sigma 1, 2, omega 1, 2, and also sigma 2, 1, omega 2, 1. So we have two of such terms which are the same. So we get a factor of 2, and then we get a factor of 2 pi, because remember that omega 1, 2 is equal to minus 2 pi. So it's quite simple. And this minus sign, it's not really important. What you would get is a minus here, but as we will see, we will get the identity, and even if you put a minus, you will still get the identity, and you can check that. So here we get e to the power 1/2 times 2 pi times the matrix M. Now, you have to be able to calculate a power of a matrix. I will not get into the details in this video, otherwise it would be too long. The idea is that this matrix can be diagonalized, and then after you expand the exponential, a lot of simplifications will be done. And by doing that, you can show that indeed you will get the identity here. So I will put a video in the appendix where I will show you, by means of an example, how to calculate the exponential of a matrix. And in this video, we have shown basically that if we rotate a vector around an axis by an angle which is 2 pi, we are going to get back the same vector, which is not really difficult to understand, right? It's quite trivial, and you might wonder why. What is the point of this? Well, actually, all of this can be generalized to spinors. But in that case, if we do the same kind of reasoning there, we get that if we rotate a spinor around an axis by 2 pi, we get a minus sign. So that's where I want to get to, and I will need some lectures to show you that indeed that's what we get. You have to be a little bit patient, but we will do it.